All right, in the last video, we talked about different treatment plans that we can do with water supply, and maybe some of them aren't necessarily needed every single time, depending on the purpose of that water, but we do have multiple ways that we can take this raw water, again, use your terms, and actually change it into something that is going to be a little bit closer to pharmaceutical grade water, which is really what we should be using most of the time when we are making or processing or developing some type of drug that's going to be injected into a person in some form or fashion. So different treatment plans do different things, right? Of course they do. That's why there's different options. And we went through the differences between each one of them in the last video. So in this particular video, I'm going to take this another step further, and we're going to talk about different types of water types. Now, you're going to see a classification that's going to happen in the laboratory side of the house, and I'm also going to describe a little bit of the manufacturing side of the house as well, just so that you get a better understanding of what goes on in each of those areas that you might find yourself working in at some point or another. All right, so as far as the lab water types, I think that a lot of people lose the bigger sight of this, and it is not my definition, it's not the company's definition. These are government definitions. These are regulatory body definitions of what acceptable water should be. And there's a couple of people that are out there that come to mind as far as organizations go, and you're going to see them listed up here at the very top. So the ASTM, ISO, USP, and CLSI, those are all abbreviations that stand for something. And I don't think that you necessarily need to remember what these abbreviations stand for, but I think it's important for me to at least mention them and talk a little bit about them. So ASTM, those letters represent the American Society for Testing and Materials. This is a regulatory body, an agency that we are going to be using quite often, especially on the laboratory side of the house. And this is talking about, hello, lab water, all right? So as far as laboratory types of supplies go, ASTM is a great resource. So standards, methods, and so forth, I'm going to be able to find those sometimes with the ASTM body. Next is ISO, which stands for International Organization for Standardization. The USP stands for United States Pharmacopoeia. And then CLSI stands for Clinical and Laboratory Standards Institute. All of these people have a say-so in particular definitions that a laboratory space might find themselves using. So if it is laboratory grade water, what does that even mean? Like, what are the restrictions? What are the requirements? Who has the say-so? Well, these organizations begin to come in mind. All right. Down here at the very bottom, you're going to see that in the laboratory testing side of the house, there are three different types of water that we often talk about, and type 1, type 2, and type 3. Type 1 water, of course, is like the A student of the classroom. So type 1, that's who I want to be. So sit up in front, pay attention, suck up to the teacher, and I'm going to get my A, right? Well, this is type 1. So type 1 is actually minimal interferences. So hardly anything in there at all, period. So I don't want any type of contamination, because that contamination can actually show up in some of our more sophisticated laboratory testing types that we do, particularly with spectroscopy and chromatography, because these instruments are very, very sensitive, and they can go very, very low as far as concentrations go. So if impurities are going to be there, those impurities can show up, and those impurities can mess with our sample data, and we don't like it when that happens. And that could come from simple water contamination, right? Everything about my sample might be okay, everything about my standard might be fine, but the water that I'm using in the laboratory is dirty enough to cause problems on the analytical instrumentation side of the house. So type 1 water is going to be often recommended and required. This is also something that I want to be using for standard preparation as well. So standards is all about this idea of how my instrument is responding to a sample. So normally what happens here is that if I know that I'm looking for something, that's great. I can find that. I can give you data on it. I can tell you what impurity is there, blah, 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 right? But in order for me to do that, this really high dollar, expensive types of equipment that could be $100,000 or more easily, well, they're kind of stupid. And I say that because, okay, they can do a job and they can do the job that you tell it to do, but that's about it. They just report numbers and they tell you what they see. That's all that goes on with equipment, really. So it's going to be our job in the laboratory side of the house to make a series of standards. And what happens is that I can number these 1, 2, 3, 4, and 5. So I'll make a set of 5 standards, and what happens is that the concentration of these standards go up and up and up and up and up. And what I'm doing is that I'm establishing a response signal. So if I analyze a very, very tiny little sample that doesn't have a lot of stuff in it at all, then I should get a tiny signal probably, right? So I can record that number down. Then if I make the next one stronger, my signal should go a little bit higher. And then if I knew the third one even stronger than that, then my signal should go even higher than that. And this establishes a relationship for me, so that way when I run my samples, I know exactly how to process those samples because I've got something to go off of on, oh, well, it ran this high. Well, if it ran this high, it's kind of close to this standard that I made, so that's probably going to be the concentrate. Well, I'm talking very loosely. We can do this much better, but it gives you an idea of what standard prep is all about. So top 1 water, that's what this whole kind of arena is going to take place with top 1 water. Top 2 water, this is great. The restrictions here are not as tight. And the reason is because this particular type of water are just for general laboratory testing. So general use water in a laboratory environment that's not going to go maybe to analytical instrumentation, that's great for top 2 water. I'm not going to have an instrument that's going to interfere with really tiny contamination amounts. And then everything from glassware washing, top 2 water is typically going to be okay with. So if I am washing beakers or graduated cylinders or any types of pieces of glassware, refluxes, condensers, bowling flask, Florence flask, whatever that I encounter in a laboratory setting, top 2 water is going to be pretty good for that. Again, it's not reaching an instrument or instrumentation that's very sensitive. It is general purpose or general kind of laboratory testing or glassware washing that we are using for top 2 water. Top 3 water, well, the restrictions here are even looser than top 2, which is even looser than top 1. And top 3 water is just preliminary water. That's how we regard that. So top 3 water could be something like CFPUA or type of outside water source that's making its way into the laboratory setting for me. And that top 3 water we know is contaminated, and we know that it is not super clean and that it cannot be used to do what we need to do with. So top 3 water is very often not necessarily raw water, but preliminary water that's coming in that needs to be cleaned up. So again, CFPUA is taking the raw water, they're processing that a number of different ways. They are producing a product that's going through my tap in the laboratory setting. Well, that water is not good enough. That water could be top 3 because this is going to be used to then filter again with more sensitive or more sophisticated pieces of instrumentation and equipment to give me a top 2 or top 1 water supply. That is eventually what we were after in a laboratory setting. So with that said, these are the types of systems that you might see in a laboratory setting because these systems are going to provide me with these really, really high quality grade water sources that I need to be using for my laboratory testing. So very often, I think for manufacturing purposes, you will often see millipore, and millipore is known in the water world and filtration world and different various aspects of laboratory testing. But this is taking a water supply and it's pumping it into a laboratory setting, and it is making sure that it can be maybe top type 1 or type 2 before we begin to use this for other purposes in the laboratory settings. Again, tap water is not going to cut it. Maybe deionized water is going to be great. Maybe that's all that you need. Maybe distilled water is going to be great. That's all that you need. But if you do want something much cleaner, then these millipore units are going to be a little bit better for you and a little more sophisticated as far as water quality and water sources go. General lab applications, buffers and pH solutions and culture media, we want to make sure that these do not have contamination, right? So of course so we want to make sure that these are as clean as possible. I don't want that contamination in any of these types of situations, because probably that media or that pH solution or that buffer solution is going to be added to the biomanufacturing processes stages. And I don't want this contaminated, because that will then contaminate the big vat of stuff that I want to keep. So anything that goes into the processing effort, it has to be super clean. I mean, we've already talked about this. We said if it comes in contact with the API or the biological that's making that, then we want to make sure that we take extra steps and extra precautions to keep it clean. That is the whole idea of sanitary and non-sanitary conditions too, right? So buffers and pH solutions and media, because they're often ingredients that get added to the process, these have to be super clean as well. As far as lab water goes, lab water is used for many different purposes. I've already talked about standards, but QC means quality control. That's what that definition means. So quality control. Quality control is this idea that I'm going to be taking samples and I'm going to be testing those samples, and I'm going to make sure that they are expected values. Like nothing has went off out in the, baseball game of the outside bleachers. I mean, this is something that I want to kind of pay attention to. I want to monitor. I want to track. I want to make sure everything is in line. Manufacturing, analytical labs all use that MilliQ system water that I kind of talked about and showed you a picture of just a few minutes ago. Making buffers, pH solutions, cultures, media, we've already talked about that as well. But standards and other solutions that are needed for the laboratory, very often this really high purity water source is going to be used for those types of situations. Now, manufacturing water is going to be a little bit different. So this was lab water. Lab water is me in the lab doing testing, using analytical instrumentation in order to make those measurements, report that data, blah, 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 blah. Manufacturing water is going to be a little different, because manufacturing is all on the manufacturing side of the house, out in the plant. So when things get made and when things get processed, what types of water are going to be used in those types of situations? That's a little different than lab water, right? So FDA recognizes 8 different types of water here, and I'm just going to quickly go through some of the titles, and I think the titles will tell you about the description. So number 1 is something that they call non-potable. This non-potable water So for this non-potable water, I mean, this is going to be something that you can't necessarily drink, all right? So I want you to think of this as water that you would not put a glass in to drink out of. That is what non-potable water is going to be. Potable water, or drinking water, is... So this picture is showing you high purity water systems, and these high purity water systems can be as big as you can imagine. So very often, sometimes these are just going to be issues that we're going to have to deal with and work around, because like I've said before, these are little mini types of water treatment plants that are located at your site location. So if I take a look at high purity water systems, first off, up here is city water, and city water is going to be the incoming water that I am receiving from my local utility source, wherever that might be, municipality, whatever the case is. CFPUA, thank you for your water. However, we're going to clean this water up a little bit better when we use it in the manufacturing and the laboratory arenas. So that city water most of the time is going to be coarse filtered, and again, that takes away any of the large particles that I might see out there. That's still a contamination problem. After it filters, then it can go through a water softener. We talked about this as well, and that will remove any calcium or any magnesium that might be built up, which are very common cations that carry positive charges in a water sample. Next up, after the water softener, activated charcoal is going to be our next, and activated charcoal charcoal is this way that we can remove organics. So once more, we talked about that as well. This is nothing new. We're just using our terms and our words now that we've learned into a little flow diagram and putting it all together. So this is removing all of the organics. So organic solvents, fertilizers, pesticides, blah, 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 blah. That's what charcoal is going to be doing. Next up, once that is now super clean, it can then easily be processed or easier processed through reverse osmosis. And this is that membrane that we discussed, and only water will be able to escape through that membrane and out the other end. We want to take care of as much, most of the time, as much contamination as we can leading up to this process, because the more of it that remains at this stage, the gunkier that reverse osmosis filter is going to become, and you're going to have to change it out more, and they're not very cheap. So if I can clean up my water pretty well up until this point, then that RO system can last for quite some time, and we don't really get any kind of problems out of it at all. Next up in this flow diagram, they do something called electrodeionization. So that deionization is just going to remove all ions now, and then ultraviolet light is going to be used, and ultraviolet light is like the ultraviolet lights in your tanning bed. It's going to kill all the germs for the most part that could be still swimming around in your water samples at this moment, and then that will lead up to what we call a high purity water sample. So that is great. That's what we want. That's kind of what we're after, at least one step in the right direction. But you can see all of the stages that have to happen here in order to get us water quality that's going to be acceptable. And this picture shows you an idea of what that type of system might look like in working conditions. And it can go much bigger than this, folks. Absolutely, it can go much bigger than this. So these are not very small areas of these companies. Water is going to be used for different purposes, and we're going to have a constant supply of it. So there are people that maybe are just assigned the water treatment area of a biomanufacturing type of company, and if so, your job is very, very important, because without you making very high quality water, the entire system and plant has to shut down. So keep that in mind when you do your work, and if you ever get mad at somebody, be ready to flip the button. No, just kidding. Don't do that to people. They'll lose their paychecks. You don't want that to happen. So water that has to be used in order to manufacture these drugs. Very often, what we've said before is that this is going to be called water for injection. So WFI, very important, because this is very often something that we need to be using in the very end. Or what we call USP purified water. So that means that it's been purified to meet the USP, United States Pharmacopoeia standards that are out there. So by the time that a consumer gets it, we know that it's going to be safe in order to use. So water for injection and USP purified water, these are very similar. But there's going to be a slight change here. So water for injection, by their definition, I'm going to read it verbatim, is the most highly purified type of water. Facilities that manufacture these injectable drugs use water for injection. Water for injection is guaranteed to be free of pyrogens, which are these large molecules from bacteria. And if those large molecules get injected into you, then this can cause fever and it can make you go to the hospital. And we do not want that to happen. So the biggest problem here are the pyrogen pieces. So this is kind of the slopped off waste that bacteria maybe that has been in your water sample, or that maybe has been used in order to make an active pharmaceutical ingredient, possibly, right? But whatever the case is, they could just be spitting out stuff, and sometimes they spit out things, and these molecules are called pyrogens, and they set up infections. They give you fevers, they get you swelling, they make you feel not very good, and then you go to the hospital and you're in there for a few days. So we cannot allow that to happen. USP purified water is highly purified based on USP standards, but it's not really meant for injectable purposes. So purified water very often doesn't really mention anything about pyrogens, and because of that, it's not necessarily injected. but it is a very common water that is used in the manufacturing processes, if that makes sense. So it really depends on the nature of the supply that we are using. Where is it going to end up? What is like the final stages of the water as we use it? Because if it is really truly water for injection, we have to make sure that those pyrogens have been removed and have been taken care of. So WFI, water for injection, is the highest purity that we are going to be regarding in the manufacturing line. And there's a couple of different ways that we can make this. Sometimes it starts off with distillation, and other times it can be reverse osmosis. Distillation, we've already talked about some of the problems, right? Distillation is this idea that we're going to heat a water sample up. That water is going to go up and over. And when it goes up and over, that requires a lot of heat. It requires a lot of energy. It requires some safety concerns versus something like reverse osmosis. So distillation is going to be a little bit better. Irradiation is kill, 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 kill. Filtration is to get rid of all of those little dead bodies that are now in that water supply, possibly due to the kill, 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 kill. And then water for injection, very often, two things have to happen here, and these are the last two that I've mentioned. It continually heats. And what this means is that it will be like your hot water heater. So it will continue to go to 80 to 90 degrees, very, very close to boiling. Boiling water is actually at 100 degrees Celsius here. So this will heat to 80 to 90 degrees, and then it will cool itself down, and then it will heat up and it cools itself down, and then it heats up and then it cools itself down. So very similar to the hot water heat. It gives you a range. That range is going to be heated up. That, of course, is going to cool down. It's not going to stay on all the time. And then it's just going to constantly circulate and continue to heat until we get ready to use it. In addition to that, we can't leave it stagnant, because if you've ever drained your hot water heater, you know what can happen. If you've drained your hot water heater, that is more like stagnant water that's going to settle to the bottom. And then when you empty that hot water heater, because you're doing your annual flush, that nobody really does except for the true hardcore hot heater fans, you're going to see all the sludge and the gunk and the rust looking stuff that's going to come out of the bottom. So we've got to continue to recirculate it, so that way we don't set up these types of problems. So that water from one vat will go and it will leave, and it will go to another vat, and then it will return, and then it will just recirculate over and over and over, normally through the storage area and the purification area. So this constantly recycles back and forth as much as possible. WFI is the most highly purified water. We've already said that. Here's a couple of vials. It says sterile water for injection, USP. And we can, of course, manufacture this and use this in bigger quantities in these tiny little vials or tiny little bottles that you are seeing here in the picture. But again, it is guaranteed to be free of pyrogens. That is the idea of water for injection. We got to get rid of those, because that slop can actually infect someone and send them to the hospital if we are not very careful with it at all. Are drugs being injected? Well, if so, the water for injection is probably needed. So I hope that makes kind of sense. After everything that we've talked about, after everything that we discussed, this goes hand in hand. If they are not meant to be injected into someone's bloodstream, then there's a chance that we probably can get away with a lower quality water. It doesn't have to be water for injection, but it still has to be very high grade. It still has to be very pure. So when I say that, I say it very loosely, because we still want those very strict water quality measures in place. But we're not necessarily too worried about the pyrogens. Only when we inject them are we worried about those problematic little children from those bacteria mommies and daddies. So if it's up to technicians, what are we responsible for when we go into the manufacturing line? Number one, we're going to monitor the conductivity. This is going to be a laboratory type of activity that you're going to do with us, and maybe you've already completed it, and if so, that's great. But we're going to monitor conductivity of water. Monitoring conductivity is all about the ions, right? So if just a little smidge of ion is going to be located there, the conductivity is going to shoot through the roof, and we can easily get thousands with our conductivity reads, or 10,000s or more with our conductivity read. So we're going to monitor conductivity constantly. We're going to look at pressures, because pressures, I mean, we're heating things up, we're storing them in tanks. Pressure is going to be built up. So we want to make sure that pressure is actually at the ideal type of situation, or PSI, both with our supply lines and inside of our holding tanks. We're going to check for correct temperatures. These are very important. Temperature is a driving force between some of the water quality issues that are out there. So we want to make sure that if we are doing WFI, or water for injection, we are heating that up the way that it needs to be heated. Check for correct pressure, we've already mentioned. Monitor levels of the water for injection. So the last thing that you want to do is not keep an eye on the fuel tank, and the manufacturing line is going to be using that water for injection, and then all of a sudden they run out. And then they're going to come back and they're going to be like, Tracy, why didn't you look at the tanks? Why didn't you tell us that we were almost empty? We need to make more of it, and we would have done it if you would have just told us. You're fired! Get out of here! Well, I hope that doesn't happen, but monitoring levels are going to be very important for me as a technician. Next up, water for injection, we said pressure and heat, right? We constantly circulate, we constantly heat. So because we are heating things like water, you want to be really careful when you are exposed to it, or when you work around it. So make sure that you do not burn yourself, please, or make sure that you do not get hit with constant hot pressure. The last thing that we want is to be scalded by the pressure, or this very kind of hot piping, or hot vats, or hot valves, or hot pumps, and blah, 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 blah. So use some common sense. Make sure that you work very careful around it. I know it's water, but water is not the problem here. It's the temperature and the pressure that it's bringing to the party with it. And it is water, so make sure you watch for slips. Again, very important. I don't want to do something silly and not pay attention to the floor, and there's a leak over in an area somewhere, and that leak now has become a puddle, and then I'm walking carelessly through the manufacturing plant, and then my shoes slip, and then down on the floor I go. So I don't want that to be an issue at all. So this is my story about water. So 1 or 2 videos here that you've had, and it's all about water for injection, which is going to be the highest purity that we can kind of get to, and very commonly used in the biomanufacturing world. And then kind of USP purified water in addition to that, and the slight differences between some of these definitions. So top 1, top 2, top 3. Top 1 is what we're after in the laboratory setting, and then of course multiple different types in the manufacturing world that we can be using, again, for different purposes. So that's where I'm going to stop this video. In the next one, we're going to continue to talk about utilities, and we're going to now focus on a different type of water, and that water is going to be called steam.